universe, the gigantic place where we all stay in a minute part called Earth. But how big it is? Was it the same what we see in present? Is it created? Will it one day end? If it is created, then how it is created? And if it will end, then how? What is the mechanism of this gigantic place? What is the building block of the universe? How these all twinkle stars are created? Lots of questions came to our mind when we watched the empty void around us.
Our knowledge about universe is just like a grain of sand. We are always trying to solve the mystery of ocean. Lots of people around the world have many ways to understand the universe and reality. Some are in religion-based and some are in philosophical-based. I also believe in religion, but I love science, particularly physics, because by unifying science and religion, in my view, we can success to reveal the secret of nature.
So once the great scientist Albert Einstein told about reality was, science without religion is lame, and religion without science is blind.
Hi, I'm Tamanna. Again came with a new documentary, How Universe is Created. This film is about how universe is created and understand the secret of its mechanism in purely scientific way. This video is little bit big. My request is please see the whole episode till end without skipping for better understanding.
Please subscribe, like, and share my video. Your support will be my inspiration. So let us start the video. If we will see around us, then we will feel that there are lots of things around us. Some are bigger in mass to us, and some are smaller in mass to us. And if we think more big way, then we can see there are 8 planets and a dwarf planet called Pluto, with a massive sun with a mass 1.989 into 10 to the power 30 kilograms. The total volume of the sun is 1.4 into 10 to the power 27 cubic meters. About 1.3 million Earths could fit inside the sun. About 333,000 times the mass of the Earth. But the sun is just average compared to other stars. Betelgeuse. A red giant is about 700 times bigger than the sun, and about 14,000 times brighter than the sun. And there are billions and billions of stars and with their planets in a single galaxy. Our solar system lays in a galaxy called Milky Way galaxy, which is our galaxy. It is very difficult to count the number of stars in the Milky Way from our position inside the galaxy. Our best estimates tell us that the Milky Way is made up of approximately 100 billion stars. These stars from a large disk whose diameter is about 100,000 light years. When we think about our galaxy, we cannot measure it our ordinary measuring system like meter and kilometer. Then we use the measurement like light year. 1 light year means the distance what light cover at 1 year interval, which speed is approximately 3 lakhs km per second. So, 1 light year is equal to 365 multiplied by 30 multiplied by 24 multiplied by 60 multiplied by 60 multiplied by 300,000 kilometer, which is around 28 lakh crore kilometers. Our solar system is about 25,000 light years away from the center of our galaxy. We live in the suburbs of our galaxy. Just as the Earth goes around the Sun goes around the center of the Milky Way. It takes 250 million years for our Sun and the solar system to go all the way around the center of the Milky Way at a speed of 828,000 km per hour. Our Milky Way is an average-sized galaxy. IC1101 galaxy, located almost a billion light years away this galaxy, and extends about 2 million light years from its core. It is 6 million light years in diameter, and it has a mass of about 100 trillion stars. And if we think bigger way, then we found cluster of galaxy. A galaxy cluster or cluster of galaxies is a structure that consists of anywhere from hundreds to thousands of galaxies that are bound together by gravity. A typical galaxy cluster contains 50 to 1,000 galaxies and has a total mass between 100 trillion and 1 quadrillion solar masses, stretching across a distance of 30 million light years. And our cluster name is Virgo cluster, in which our average-sized galaxy, Milky Way, stays. And if we think bigger way, then we found superclusters. A supercluster called Laniakea supercluster, in which our cluster Virgo cluster, 1 of 1,000 part of it. Scientists imagine that supercluster Laniakea is home to the Milky Way and approximately 100,000 other nearby galaxies. The number of superclusters in the observable universe is estimated to be 10 million. Finally, our reach is still our observable universe. This from Big Bang to till now, what we can see or light can reach near us. The observable universe is a spherical region of the universe comprising all matter that can be observed from Earth or its space-based telescopes and explorator probes at the present time. Because electromagnetic radiation from these objects has had time to reach the solar system and Earth since the beginning of the cosmological expansion. There are more than 2 trillion galaxies in the observable universe. But our observable universe is one part of our whole universe. According to the theory of cosmic inflation, initially introduced by its founder, Alan Guth, and by D. Cazanes, So, the observable universe is a sphere with a diameter of about 28.5 gigaparsecs, or 93 billion light years, or 8.8 into 10 to the power 26 meters. Assuming that space is roughly flat, this size corresponds to a moving volume of about 3.57 into 10 to the power 80 meter cube. According to the theory of cosmic inflation initially introduced by its founder Alan Guth, that would suggest that at present the entire universe size is at least 3 into 10 to the power 23 times the radius of the observable universe, and some theory tells it may be infinity. But here question may arise, is it only universe? Which is our universe, or there are infinity of universes? Lots of physicists believe there may be infinity numbers of universes. But let we have only one universe. Then also same question may arise. Why is it created? How it is created? What is the mechanism behind this entire moving and non-moving object? How this works so systematically? When this thing will end? What about time? Why it is going only in forward direction? And people try to understand this thing. And this question creates various religions. The entire unexplained miracle has one answer in various religions, that God created this, God ruling this, and God will end this. Before going to scientific analysis, we are going to little bit religious analysis, because
Every religion have a belief on creation of universe and understanding of reality in different way. Among them, one of the religions where we get the creation of universe is Hinduism, which I belong to.
in this religion, inside religious book Veda, all the modern unexplained theories like multiverse, different timeline, multistellar movement, different dimension, age of universe, when and how universe is created, when it will destroy, all are written. Universe is created from a supreme god called Shiva. Other names of Lord Shiva is Mahakal, or Supreme Time, and his wife Ma Shakti, or Queen of Energy. Supreme Time or Mahakal have no shape, and he kept still like a frozen river for an infinity long period. And when he decided to form a universe, he and his wife Mahashakti pop up and create Lord Vishnu, who is another supreme god, who sleeps on a large ocean. Here, we should think ocean does not mean a large reservoir of water. Maybe some other thing like ocean of energy in a very big cosmic level. Lord Vishnu's responsibility is to take care of the universe. He has 4 hands to do so. Maybe just like 4 fundamental forces by which the universe governed. From his navel, a lotus created, and in that lotus, in a cosmic egg, Lord Brahma created, just like Big Bang. And from Lord Brahma, all are created. Another popular religion is Islam. Quran's story of the creation of the world in the context of science, and believe that the scientific theory of an expanding universe is described in Surat Al-Dariyat. We have built the heaven with might, and we, it is who expanded. Ancient Greek. The earliest cosmological models of the universe were developed by ancient Greek and Indian philosophers and were geocentric, placing Earth at the center. In 340 BC, the Greek philosopher Aristotle, in his book On the Heavens, demonstrated a good argument for believing that the Earth is a round sphere rather than a flat plate. First, he realized that eclipses of the moon were caused by the Earth coming between the sun and the moon, and the Earth's shadow on the moon was always round, which would be true only if the Earth was spherical. If the Earth had been a flat disk, the shadow would have been elongated and elliptical, unless the eclipse always occurred at the time when the sun was directly under the center of the disk. But Aristotle taught a wrong concept, that the Earth is stationary and that the sun, the moon, the planets, and the stars moved in circular orbits about the Earth. He believed this because he felt, for mystical reasons, that the Earth was the center of the universe, and that circular motion was the most perfect. In 14th century, the more precise astronomical observations led by Nicolaus Copernicus to develop the heliocentric model with the sun at the center of the solar system. Then two great astronomers, the German Johannes Kepler and the Italian Galileo Galilei, started publicly support to the Copernican theory in developing the law of universal gravitation. Sir Isaac Newton built universal gravitational formula upon Copernicus' work as well as Johannes Kepler's laws of planetary motion and observations by Tycho Brahe. Then in 19th century, a great genius tried to understand this entire question. He was Albert Einstein. He found universe is made of matter, which have a mass, maybe how big or how small, but have a physical existence, and regulating by certain laws. Energy which have no mass but physical existence. Light having a physical existence but no mass running with a constant speed, 3 lakhs km per second. And two other things, space and time, which have no mass, but two are real things which exist combined to form space and time, which is the fabric of cosmos. He discovered that mass and energy are same thing and gave a formula E = mc², which means an object having a mass is just a form of energy, and how much? That is the product of its mass and square of speed of light. Great! But what about space and time? And the genius in his 10 years of research found that space and time are also two real things which cannot feel or see. But it regulates all matter in this universe, and both two are combined, making an elastic fabric called space-time. This fabric bends and twists in present of mass. Or simply we can say, this is the fabric of cosmos. Mass decide how to curve the cosmos fabric, or space-time decides which path the object to be moved. And the gravity is just a result of that bend and twist of space-time. He also gives us a formula that how much the space curve in present of certain mass or energy called as Einstein field equation.
So let us understand what 21st century telling how universe created and how it is working in present days and how it will end. Before going to the topic, let us understand what is universe.
The universe is defined as the totality of existence, or everything that exists, everything that had existed, and everything that will exist. There are a lot of theory about creation of universe, and every theory has their specific reason for existence, which we'll discuss in further episodes. But the best proven theory of creation of our universe is Big Bang. Basically, Big Bang is an event. This theory was born of the observation that other galaxies are moving away from our own at great speed in all directions, as if they had all been propelled by an ancient explosive force. Georges Lemaitre, Roman Catholic priest, physicist, and astronomer. He is usually credited with the first definitive formulation of the idea of an expanding universe, and what was to become known as the Big Bang theory of the origin of the universe. Big Bang model states that before Big Bang, universe was a gravitational singularity. Infinitively hot and dense primeval atom or primeval dough, or simply a point. A singularity in solutions of the Einstein field equations is one of two things. A situation where matter is forced to be compressed to a point, or a space-like singularity. A gravitational singularity or space-time singularity or simply singularity is a location in space-time where the gravitational field of a celestial body is predicted to become infinite by general relativity in such a way that it does not depend on the coordinate system. Just before around 13.8 billion years ago, there was a Big Bang. But why we believe this theory? Because the Big Bang model accounts for observations such as the correlation of distance and redshift of galaxies, the ratio of the number of hydrogen to helium atoms, and the microwave radiation background. In 1929, Edwin Hubble's experimental observations discovered that, relative to the Earth, all galaxies are receding in every direction at a velocity which is homogeneous and isotropic way. In June 2016, NASA and ESA scientists reported that the universe was found to be expanding 5% to 9% faster than thought earlier, which is based on studies using the Hubble Space Telescope. So, if we run the time in backward, then the entire galaxy are migrated from one place or they have a single origin. Or a simple way, when we measured the rate of expanding universe, then we found that before 13.8 billion years ago, all should migrate from a single point, or they have a single origin. A tiny, extremely dense and hot or primeval atom or primeval dough. Another direct proof which we found from cosmic microwave background. Cosmic microwave background was first found by accident in 1965. Two researchers, Arno Penzias and Robert Wilson in Bell Telephone Laboratories, were creating a radio receiver and were puzzled by the noise it was picking up. They soon realized this noise came uniformly from all over the sky. Penzias and Wilson both received the 1978 Nobel Prize in Physics for this discovery. The cosmic microwave background is leftover radiation from the Big Bang or the time when the universe began. The CMB represents the heat left over from the Big Bang. You cannot see the CMB with your naked eye because it is invisible to humans. But it is everywhere in the universe, and its radiation is visible in the microwave part of the electromagnetic spectrum. A more detailed map came in 2003 courtesy of the Wilkinson Microwave Anisotropy Probe. This launched in June 2001 and stopped collecting science data in 2010. The first picture pegged the universe's age at 13.8 billion years and also revealed a surprise that the oldest stars started shining about 200 million years after the Big Bang. Scientists followed up those results by studying the very early inflation stages of the universe in the trillionth second after formation, and by giving more precise parameters on atom density, the universe's lumpiness and other properties of the universe shortly after it was formed. They also saw a strange asymmetry in average temperatures in both hemispheres of the sky, which explained the uniform expansion and isotropic expansion of universe. In 2013, data from the European Space Agency's Planck Space Telescope was released, showing the highest precision picture of the CMB yet. Scientists uncovered another mystery with this information, that the fluctuations in the CMB at large angular scales did not match the predictions. Planck telescope also confirmed what WMAP saw in terms of the asymmetry and the cold spot that was bigger than expected. So what happened in Big Bang, or how our universe is created? The model includes a single originating event called the Big Bang, which was not an explosion but the abrupt appearance of expanding space-time in an isotropic way, which contained radiation at temperatures of around 10 to the power 15 Kelvin. This isotropic nature of the expansion was direct proof that it was the space itself expanding, not the bodies in space that were simply moving further outward and apart into an infinitely larger empty void. This was a view of Einstein's general relativity that space is an elastic fabric. So during very initial time, the universe was very small, nearly as the size of an atom or primeval atom or primeval dough. And it was extremely dense and hot. And then, suddenly a single originating event called the Big Bang happened. That the universe subsequently expanded isotropically. But here is a question. If during Big Bang, universe was very small, nearly as the size of an atom, and extremely dense, which is far denser than usually required for a black hole. But why did not it collapse into a black hole? This because commonly used calculations for gravitational collapse are usually based upon objects of relatively constant size, such as stars, and do not apply to rapidly accelerating expanding space such as the Big Bang. But till now there is some unsolved question. From where the tiny, extremely dense and hot or primeval atom or primeval dough came? Is that the universe was self-creating? Did God created it? Or only natural laws and forces operating in the world, and that nothing exists beyond the natural world? There is still an answer to the scientists that time also started during that event. So, if time does not exist before Big Bang, then the question is meaningless, that where the tiny atom came. And the time began with a zero-energy cosmic singularity universe. Negative energy became dark energy, and positive energy became space. And all four fundamental forces, antimatter, matter, and the final sum became equals to zero. But still there are lots of theories like string theory, multiverse, Big Rip, Big Crunch, Big Bounce, holographic principle, bubble universe, but those are still to be proved. Finally, due to Big Bang theory have sufficient evidence, so it is widely acceptable. If we will try to understand the Big Bang model, then we have to understand Lambda-Cdm model, which referred to as the standard model of Big Bang cosmology. It is the simplest model that provides with a cosmological constant lambda and cold dark matter. Lambda-Cdm model. Lambda-Cdm told universe contains three major components. First, a cosmological constant denoted by lambda and associated vacuum energy or dark energy in empty space. That is used to explain the contemporary accelerating expansion of space against the attractive effects of gravity. A cosmological constant has negative pressure.
Second, the postulated cold dark matter. Dark matter postulated is to account for gravitational effects observed in very large-scale structures such as clustering of galaxies, which cannot be possible without it. During the 1970s and the 1980s, various observations showed that there is not sufficient visible matter in the universe, which will create the apparent strength of gravitational forces inside and between galaxies. When mass profiles of galaxies are calculated from the distribution of stars in spirals and mass-to-light ratios in the stellar disks, that time we observed that they do not match with the masses derived from their observed rotation curves and the law of gravity. And the solution is to this raise a hypothesis that the existence of dark matter and to assume its distribution from the galaxy center out to its halo. Otherwise, it needs to be modified Newtonian dynamics or modifying the laws of gravity. The dark matter particles interact with each other and other particles only through gravity and possibly the weak force. And the dark matter is responsible to produce gravity for construction of galaxy and cluster. Dark matter constitutes about 26.5% of the mass energy density of the universe.
And third is ordinary matter. The remaining 4.9% comprises all ordinary matter observed as atoms, chemical elements, gas, and plasma, the stuff of which visible planets, stars, and galaxies formed. Most of ordinary matter in the universe is unseen. The visible stars and gas inside galaxies and clusters account for less than 10% of the ordinary matter. The early phases of the Big Bang are subject to much speculation because astronomical data about them are not available. In the most common models describe that the universe had filled homogeneously and isotropically with a very high energy density and huge temperatures and pressures. A brief period extending from time 0 to 1 Planck time unit of approximately 10 to the power minus 43 seconds. That period is called Clock Epoch. That time the universe was only about 10 to the power minus 35 meters wide and consequently had a temperature of approximately 10 to the power 32 degrees Celsius. And in initial stage of Big Bang, 4 fundamental forces of nature were in combined stage. They were gravity, strong nuclear, weak nuclear, electromagnetic force. During starting of the Planck epoch or zero time, all types of matter and unified forces and space-time foam had been combined into a dense state as a cosmic singularity, and among them gravity, which is currently the weakest by far of the 4 known forces. It is believed that gravity was as strong as the other fundamental forces at that time. The best assumption that in this time period all matter, energy, space and time was exploded outward from the original singularity. But still it is a mystery for science that whether it was a pop-up of universe from singularity at time 0 or not. After 10 minus 43 seconds of universe pop-up, grand unified epoch started. At the beginning, at 10 to the power minus 43 seconds, Planck epoch was ended by the grand unification epoch, where the gravitational force separated from the other forces as the universe's temperature fell. At this time, the universe was pure energy stage, too hot, which was not suitable for any particles to create. At approximately 10 to the power minus 37 seconds after Big Bang, the universe started to expand very rapidly, which is called as cosmic inflation, during which the universe grew exponentially faster than the speed of light, and temperatures dropped by a factor of 100,000. And the microscopic quantum fluctuations occurred. But what is quantum fluctuation? In quantum physics, quantum fluctuation or vacuum state fluctuation is a temporary change in the amount of energy in a point in space, which create off particle and antiparticle pairs of virtual particles. Simply, we can say a particle pair can pop out of the vacuum for an extremely short time interval. But why inflation happened and why it has stopped, or why this theory need to be added in Big Bang? Do you know one thing? Mythology always runs with belief, but science needs proof that may be experimentally or theoretically. And the inflation happened because of phase transition. Let us understand phase transition. There are 4 states of matter in the universe: plasma, gas, liquid, and solid. There are 6 distinct changes of phase which happens to different substances at different temperatures. These 6 changes are: freezing. The substance changes from a liquid to a solid. Melting. The substances changes back from the solid to the liquid. Condensation. The substance changes from a gas to a liquid. Vaporization. The substance changes from a liquid to a gas. Sublimation. The substance changes directly from a solid to a gas without going through the liquid phase. Deposition. The substance changes directly from a gas to a solid without going through the liquid phase. A phase is a distinctive form of a substance, and matter can change among the phases. It may take extreme temperature, pressure, or energy, but all matter can do phase change. Simply, these changes occur when sufficient energy is supplied to the system, or a sufficient amount is released, and also occur when the pressure on the system is changed, and when the gravity is separated from the primeval dough. That time also same thing had happened. At this moment, space-time had separated and a tremendous amount of energy was released. This energy produced an overpressure that it had applied to space-time itself. At a time around 10 to the power minus 36 seconds, another epoch started. That is called electroweak epoch. When the strong nuclear force separated from the other forces and only the electromagnetic force and weak nuclear force remained unified. Inflation stopped at around the 10 to the power minus 33 to 10 to the power minus 32 seconds after Big Bang. And till that time, universe volume increased by a factor of at least 10 to the power 78. an expansion of distance by a factor of at least 10 to the power 26 in each of the 3 dimensions, which is equivalent to expanding an object 1 nanometer or about half the width of a molecule of DNA in length to approximately 10.6 light years, about 10 to the power 17 meter or 62 trillion miles long. And the universe again expanded in a regular way, what is presently happening. But why inflation added in Big Bang model? Because due to the horizon problem. It means the CMB gives us the data that both sides of the horizon are the same and isotropic. When we calculate the speed of expansion, we found the expansion far more than speed of light. But how it is possible? Because relativity does not allow this. But here our space is expanding, not object is moving, so our Einstein is saved. Then another question may come, what about energy density? If the expansion is so high, then the energy density might be low with that expansion. But experiment told that the energy density is equal. What about energy conservation? Then we will have to go to quantum physics, where there is negative energy also. Scientists believe that there may be the negative energy which created by gravitational energy, and it increased with positive energy. That means universe created from zero energy and expand with increase of positive energy parallel with increased negative energy, where the final value is zero. Grand unified era. When gravity was separated from the other 3 fundamental forces, then matter made its first appearance. During this era, matter appeared as a composite form called grand unified matter, which is a combination of leptons, quarks, and photons. But during this era, it was too hot and violent for matter to survive in the form of leptons and quarks. But why can't matter remain stable at this point in the universe's evolution? This involves the concept equilibrium, the balance between particle creation and annihilation. During this epoch, energy was converted directly into mass in the form of a matter and antimatter particle pair, such as an electron-positron pair. But due to high energy and high temperature, the conversion from energy to mass was unstable compared to mass to energy conversion, because the created mass need to be high in mass to match the energy used. Or, in other words, when temperatures are high, the matter is unstable and energy is stable. So, matter that formed in the early universe quickly collided with the other matter or energy and converted back into energy. As the volume of the universe increased with the expansion respectively, the time between collisions matter with photons had also increased. Or we can say the increased time was suitable for matter to interact with matter had increased. The universe started to move forward from a pure energy-dominated domain to matter-dominated domain. After GUT matter forms, the next phase was for GUT matter to decay into lepton. Lepton matter will become our old friends, the electron and neutrino and the antiparticles. But quark matter is unusual because of the property of quark confinement. After approximately 10 to the power minus 12 seconds after the Big Bang, the quark epoch started. To understand quark epoch, we have to understand the fundamental of particle physics. In particle physics, we knew all substances are either element or compound. Element means till atom level it is the same substance, just like carbon, iron, hydrogen, oxygen, or all the 118 matter in periodic table. When two or more elements combine, they form compound, like water. This is made of hydrogen and oxygen. Similarly, various compounds are available in our Earth, but atom is not the smallest particle of an element. It is made of subatomic particles like electron, proton, and neutron. And further, those electron, proton, neutron are made of either single types elementary particle or made of composite, means made of more than one elementary particle bound together. These are called subatomic particles. These subatomic particles are 6 flavors of quarks. They are up, down, strange, charm, bottom, and top. 6 types of leptons. They are electron, electron neutrino, muon, muon neutrino, tau, tau neutrino. 12 gas bosons particles, which are also called force carriers particles. They are photon particle for electromagnetism, the 3 W and Z bosons particles for the weak nuclear force, and the 8 gluon particles for the strong nuclear force, the Higgs boson, and another particle, graviton, but now is not confirming that it exists. Quarks have various intrinsic properties, including electric charge, mass, color, and spin. But quarks are smaller than photons, so they have no color, but a scientific virtual property. And about this property, we will discuss in my upcoming video, Quantum Physics, more briefly. Let us again come to the topic, the quark epoch. After approximately 10 to the power minus 12 seconds after the Big Bang, the quark epoch started. The quark epoch had a lasting from 10 to the power minus 12 to 10 to the power minus 6 seconds. When the universe has cooled down to about 10 quadrillion degrees and the 4 fundamental forces are separate, the universe had a higher degree of stability. It is here we begin to see the rapid formation of quarks and antiquarks. These particles collide and annihilate one another on impact. About in every billion quark-antiquark collisions, one quark was not annihilated. This asymmetry of quarks to antiquarks is the reason why mass exists today. Otherwise, particles may have just collided and destroyed each other until the end of time. The buildup of quarks and the presence of gluons, which is boson force carrier particle, caused the consistency of the universe to be a densely populated quark-gluon soup. It is named as such because the present observation of particle collisions, the Large Hadron Collider in Geneva, Switzerland, have given physicists reason to believe that the universe was was a plasma at this point in time. Until these observations, the prevailing theory was that the universe was a gas during the Clock Epoch. But having such a beautiful proven theory, why scientists are divided in search of other theory of universe creation? Because in present day, due to quantum physics, we knew that the subatomic matter can pop out from vacuum with the antimatter pairs. But these exist for very little time as billionth part of second and again collides each other to form photons. That process is called annihilation. The total energy and momentum of the initial pair are conserved in the process and distributed among a set of other particles in the final state. Because the antiparticles which formed have exactly opposite additive quantum numbers from particles. So, the sums of all quantum numbers of such an original pair are zero. Hence, any set of particles may be produced whose total quantum numbers are also zero, as long as conservation of energy and conservation of momentum are obeyed. This is like 10 rupees you borrow from someone and buy an apple. Again, you sell that apple and return the money to the same. The final result is zero. And similarly, you can borrow billion rupees, do the same, the final result is zero. No formula of math is breaking. Similarly, subatomic matter borrow energy to create matter-antimatter pairs. And again, flashback to vacuum energy, so no loss breaks. But the question is, why matter came to dominate? The most unsolved question of nature that scientists have yet to discover with proof. Let us understand what it is. Universe produced equal numbers of matter and antimatter particles, and at any particular time. If the process of pair production were to stop, then all matter and antimatter would eventually collide, and the universe will be composed only of photons. In other words, since there are equal numbers of matter and antimatter particles had created by pair production, then why there is mostly of matter inside the universe? Where is all antimatter? Why not all the matter and antimatter should have cancelled out to make the universe an ocean of photons? Theoretical physicists are thinking that an imbalance between particles and antiparticles must have developed during the primordial expansion. But why they are thinking so? Because we can't go back in time and count the number of matter or antimatter pairs. But we have a technology to count the number of cosmic background photons that remain after the annihilations. That is the echo of the Big Bang. When a matter-antimatter pairs annihilate each other, they produce photons with a release of energy, which creates certain echoes in the electromagnetic field. When we decode the echoes of CMB photons, we found a value of 1 matter particle for every 10 to the power 10 photons. This means the asymmetry between matter and antimatter was only 1 part in 10 billions. This means that for every 10 billion antimatter particles, there are 10 billion and 1 matter particles, an asymmetry of 1 particle out of 10 billion. And the end result is that every 10 billion matter-antimatter pairs annihilated each other, leaving behind one matter particle, and 10 billion photons that made by cosmic background radiation. This ratio of matter to photons is called the Baryon number. And by this matter, all matter in our universe is created. Matter and antimatter that favors the survival of matter. Theoretical physicist Stephen Hawking believes that as the universe continued to expand and the temperature to drop, the rate at which electron and anti-electron pairs were being produced in collisions would have fallen below the rate at which they were being destroyed by annihilation. So, most of the electrons and anti-electrons, leaving only a few electrons left over. The neutrinos and antineutrinos, however, would not have annihilated with each other, because these particles interact with themselves and with other particles only very weakly. So, they should still be around today. If we could observe them, it would provide a good test of this picture of a very hot early stage of the universe. Unfortunately, their energies nowadays would be too low for us to observe them directly. However, if neutrinos are not massless but have a small mass of their own, as suggested by some recent experiments, we might be able to detect them indirectly. They could be a form of dark matter. However, no one is sure what those processes were and how they worked. Identifying effects associated with the matter-antimatter asymmetry is now one of the main research areas in fundamental physics. Antimatter particles are created in ultra-high-speed collisions. In the first moments after the Big Bang, only energy existed. One theory suggests that more normal matter was created than antimatter in the beginning, so that even after mutual annihilation, there was enough normal matter left to form stars, galaxies, and us. But it is true that if matter and antimatter are created and destroyed together, it seems the universe should contain nothing but leftover energy. Nevertheless, a tiny portion of matter, about 1 particle per billion, managed to survive. This is what we see today. In the past few decades, particle physics experiments have shown that the laws of nature do not apply equally to matter and antimatter. Physicists are keen to discover the reasons why it is so. Andrei Dmitrievich Sakharov, Russian nuclear physicist and Nobel laureate. In 1967, Andrei Sakharov proposed a set of 3 necessary conditions that a baryon generating interaction must satisfy to produce matter and antimatter at different rates. They are Baryon number violation, C symmetry and CP symmetry violation, interactions out of thermal equilibrium. The last condition is more interesting because the rate of a reaction which generates baryon asymmetry must be less than the rate of expansion of the universe. In this situation, the particles and their corresponding antiparticles do not achieve thermal equilibrium due to rapid expansion decreasing the occurrence of pair annihilation, but all are yet to be proved. A part of Andrei Shekharov theory, some other theory also explains the imbalance of matter and antimatter puzzle. Among them, the most interesting one is mirror anti-universe, which tells that the Big Bang had generated a universe-anti-universe pair. Our universe flowing forward in time while our mirror counterpart flowing backward in time, which is made of antiparticle galaxy. Now again come to the topic. When the preceding electroweak epoch ended, as the electroweak force separated into the weak force and electromagnetism. During the Quark Epoch, the universe was filled with a dense, hot quark gluon plasma containing quarks, leptons, and the antiparticles. At temperatures, quark-gluon plasma was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, which is about 100,000 times hotter than the center of the Sun. Collisions between particles were too energetic to allow quarks to combine into mesons or baryons. The Quark Epoch ended when the universe was about 10 to the power minus 6 seconds old. Baryon Genesis. To understand baryon genesis, we have to understand about subatomic particle in particle physics. In particle physics, a hadron is a subatomic composite particle made of two or more quarks held together by the strong force. Hadrons are categorized into two families. Baryons made of an odd number of quarks, usually 3 quarks, and mesons made of an even number of quarks, usually 1 quark and 1 antiquark. Protons and neutrons are examples of baryons. Pions are an example of a meson. After 10 to the power minus 6 seconds of universe creation, hadron epoch started. When the universe was around 1 trillion degrees, which is about 100,000 times hotter than the center of the Sun, which allowed quarks to combine and form hadrons. And this happened due to equilibrium process. The equilibrium process is the balance between the strong force binding quarks into protons and neutrons versus the splitting of quark pairs into new quark pairs. When the temperature of the universe dropped to the point that there was not enough energy to form new quarks, the current quarks were able to link into stable triplets. And hadron created as baryon, mostly proton and meson like electron and neutrinos. The protons began to collide with electrons at extremely high speed, which formed neutrons. Neutrinos are massless particles given off from the collision of protons and electrons that are travel near the speed of light. Then came lepton epoch. It started roughly 1 second after the Big Bang, after the majority of hadrons and antihadrons annihilated each other at the end of the hadron epoch. Before understanding the lepton epoch, let us understand what lepton is. Lepton is another important elementary particle in an atom. In particle physics, a lepton is a subatomic particle of half-integer spin that does not undergo strong interactions or strong nuclear force, but responds to the electromagnetic force, weak force, and gravitational force. Two main classes of leptons exist. They are charged leptons and neutral leptons. Charged leptons are three types. They are electron, muons, and taus. And neutral leptons are three types. They are electron neutrino, muon neutrino, tau neutrino. Electrons have the least mass of all the charged leptons. The heavier muons and taus will rapidly change into electrons and neutrinos through a process of particle decay. Thus, electron or stable lightest leptons have a mass only 1 by 1840 part of a proton. Electron is the most common charged lepton in the universe, whereas muons and taus can only be produced in high-energy collisions, such as those involving cosmic rays and those carried out in particle accelerators. During the lepton epoch, the temperature of the universe was still high enough which had created lepton and antilepton pairs. And approximately 10 seconds after the Big Bang, the temperature of the universe had fallen to the point where lepton or antilepton pairs were no longer created. And then, most leptons and antileptons were eliminated in annihilation reactions by leaving a small residue of leptons and a vast amount of photons. Or we can say the preceding electroweak epoch ended as the electroweak force separated into the weak force and electromagnetism. As a result, the mass of the universe was then dominated by photons as it entered the following photon epoch. In physical cosmology, the photon epoch was the period in the evolution of the early universe in which photons dominated the energy of the universe. Then starts primordial nucleosynthesis. Primordial nucleosynthesis is believed by most cosmologists to have taken place in the interval from roughly 10 seconds to 17 minutes after the Big Bang. Big Bang nucleosynthesis theory is first introduced by Ralph Alpher in the 1940s. Alpher published the Alpher-Bethe-Gamma paper that outlined the theory of light element production in the early universe. During the 1970s, there was a major puzzle in that the density of baryons as calculated by Big Bang. Nucleosynthesis was much less than the observed mass of the universe based on measurements of galaxy rotation curves and galaxy cluster dynamics. And this puzzle was resolved by postulating the existence of dark matter. Let us know what had happened in primordial nucleosynthesis. Roughly 10 seconds after the Big Bang, there was many photons had sufficient energy to form photodissociation deuterium. Deuterium is also known as heavy hydrogen, which is an isotope of hydrogen. The nucleus of a deuterium atom contains one proton and one neutron. Nearly all deuterium found in nature was produced in the Big Bang. The primordial ratio of hydrogen 1 to deuterium, about 26 atoms of deuterium per million hydrogen atoms, has its own origin from that time. And the ratio in Earth's ocean is 156 atoms of deuterium per million hydrogen atoms. Deuterium is thought to have played an important role in setting the number and ratios of the element that were formed in the Big Bang. During nucleosynthesis, temperature was high enough that the mean energy per photon particle was greater than the binding energy of weakly bound deuterium. Therefore, any deuterium that was formed was immediately destroyed. This situation is known as the deuterium bottleneck. When the temperature downed at about a temperature equivalent to 100 kiloelectron volt, there was a sudden burst of element formation, first deuterium, which immediately fused to helium. At 20 minutes after the Big Bang, the universe became too cool for any further nuclear fusion and nucleosynthesis to occur. And due to the nuclear fusion, heavier atoms like tritium, helium-3, helium-4, trace amounts of lithium, beryllium, and insignificant amount of carbon or any other elements heavier than carbon began to appear, which made key roles in formation of stars. At the same time, the failure of much nucleogenesis during the Big Bang ensured that there would be plenty of hydrogen in the later universe available to form long-lived stars. Example, our Sun. Once the thermal energy dropped below 0.03 mega electrovolt, after nucleosynthesis ended, but still photon epoch continued. For the remainder of the photon epoch, the universe contained a hot dense plasma of nuclei, electrons, and photons. At around 47,000 years after the Big Bang, the universe more cooled. Its behavior began to be dominated by matter rather than radiation. As a result, photons no longer interacted frequently with matter. The universe became transparent, and the cosmic microwave background radiation was created, and then structure formation took place. As the universe expanded, the energy density of electromagnetic radiation decreased more quickly than does that of matter, because the energy of a photon decreases with its wavelength. At around 47,000 years, the energy density of matter became larger than that of photons and neutrinos, and began to dominate the large-scale behavior of the universe. This marked the end of the radiation-dominated era and the start of the matter-dominated era. Then came matter-dominated era. It is believed that at about 100,000 years, helium hydride is the first ion formed. 370,000 years after the Big Bang, the temperature of the universe fell to the point where nuclei combined with electrons to create neutral atoms. And the fraction of free electrons and protons as compared to neutral hydrogen decreased to a few parts in 10,000. and the universe became transparent for the first time, and photons epoch ended and recombination epoch started. Matter-dominated era. Between 47,000 years and 9.8 billion years after the Big Bang, the energy density of matter exceeded both the energy density of radiation and the vacuum energy density. In this period, at about 370,000 years after the Big Bang, recombination epoch came. Before recombination, photons were not able to freely travel through the universe, as they constantly scattered off the free electrons and protons. Due to scattering, causes no information in redshift at cosmic background model, which is called photons barrier at a redshift. Once recombination had occurred, however, the mean free path of photons greatly increased due to the lower number of free electrons. Shortly after recombination, the photon mean free path became larger than the Hubble length, and photons traveled freely without interacting with matter. Recombination epoch. In this epoch, the charged free electrons and protons first became bound to form electrically neutral hydrogen atoms. Because direct recombination to the ground state or lowest energy state of hydrogen are very inefficient. These hydrogen atoms generally form the electrons in a high energy state, and the electrons quickly transition to their low energy state by emitting photons. Because the neutral hydrogen that formed was transparent to light, those photons which were not captured by other hydrogen atoms. And first time photon travel a longer distance, which we are detecting today as radio waves, and form the cosmic microwave background, or CMB. But here is the most important law of nature worked, that nothing could be perfect in the universe. Or we can say, perfection does not exist. And the universe was also not perfectly uniform. The universe was slightly lumpy to form galaxies, and later on from the interval gravity of the lumps. Gravity is symmetrical, so it needed some initial density variations to provide some direction to where surrounding matter could be attracted. And similar things celestial engineering worked to construct of galaxy and superstructure what we see today. The proof of this thing we found from Kobe satellite. The Kobe satellite found slight variations in the brightness of the background radiation of about 1 part in 100,000. The slight variations exist because some part of the universe was slightly denser than other parts. The slightly denser regions had more gravity and attracted more material to them, while the expansion occurred. Over time, the denser regions got even denser and eventually formed galaxies about 1 billion years after the Big Bang. The slightly less dense places got even emptier as gravity increased the contrast between the denser places and less dense places. Dark Ages. This period, known as the Dark Ages, began around 370,000 years after the Big Bang. During the Dark Ages, the temperature of the universe cooled from some 4000 Kelvin to about 60 Kelvin. After recombination and decoupling, the universe became transparent and had cooled enough to allow light to travel long distances. But there was no light-producing object such as stars and galaxies. Because stars and galaxies are formed when dense regions of gas forms due to the action of gravity. And this takes a long time within a near uniform density of gas and on the scale required. So it is estimated that stars did not exist for perhaps hundreds of millions of years after recombination. Only two sources of photons existed. The photons released during recombination or decoupling as neutral hydrogen atoms formed, which we can still detect today as the cosmic microwave background or CMB, and photons occasionally released by neutral hydrogen atoms known as the 21 cm spin line of neutral hydrogen. The hydrogen spin line is the microwave range of frequencies, and within 3 million years, the CMB photons had redshifted out of visible light to infrared. From that time until the first stars, there were no visible light photons. Other than perhaps some rare statistical anomalies, the universe was truly dark. The first generation of stars, known as population 3 stars, formed within a few hundred million years after the Big Bang. These stars were the first source of visible light in the universe after recombination. Structures may have begun to emerge from around 150 million years, and early galaxies emerged from around 380 to 700 million years. We do not have separate observations of very early individual stars. The earliest observed stars was discovered as participants in very early galaxies. As they emerged, the Dark Ages gradually ended. Because this process was gradual, the Dark Ages only fully ended around 1 billion years as the universe took its present appearance. There is also currently an observational effort underway to detect the faint 21 cm spin line radiation, as it is in principle an even more powerful tool than the cosmic microwave background for studying the early universe. In the earliest stages of the universe, tiny fluctuations within the universe's density led to concentrations of dark matter gradually forming. Ordinary matter, attracted to these by gravity, formed large gas clouds and eventually stars and galaxies. Where the dark matter was most dense and voids where it was least dense, after around 100 to 300 million years, the first stars formed known as population 3 stars, which was the formation of the first stars. Under current cosmological models, all matter created in the Big Bang was mostly hydrogen, that is 75%, and helium, that is 25%, with only a very tiny fraction consisting of other light elements, that implies lithium and beryllium. When the universe had cooled sufficiently, the first stars were born as population 3 stars, without any contaminating heavier metals. And such stars had their stellar masses became hundreds of times more than that of the Sun. These massive stars also developed very quickly, and their nucleosynthesis process created the first 26 elements, up to iron in the periodic table. Stars too massive to produce pure instability supernovae would have likely collapsed into black holes. Here, some matter may have escaped during this process in the form of relativistic jets, and this could have distributed the first metals into the universe. Formation of the observable stars. The oldest observed stars, known as population 2, have very low metallicities. In astronomy, metallicity is the elements present in an object that are heavier than hydrogen or helium. Astronomers use the word metals as the convenient short term for all elements except hydrogen or helium. Stars and nebula with relatively high percentages of carbon, nitrogen, oxygen, and neon are called metal-rich in astrophysical terms, even though those elements are non-metals in chemistry. Population 2 stars and clusters which formed about 10 billion to 13 billion years ago. These stellar objects are relatively rich in hydrogen and helium, but are poor in elements heavier than helium, containing 10 to 100 times less of these elements than population 1 stars. Population 2 stars are found in the halos of spiral galaxy. Large number of these objects also occur in elliptical galaxies. As those stars died, they returned metal-enriched material to the interstellar medium via planetary nebula and supernova. Population 1 stars consists of younger stars that formed about present to 10 billion years ago. Certain stars, such as the very hot population 1 star, occur near and in the arms of the Milky Way system and other spiral galaxies. They also have been detected in some young irregular galaxies. Population 1 objects are thought to have originated from interstellar gas that has undergone various kinds of processes, including supernova explosions. Such stars contain highest metals such as iron, nickel, carbon, and certain other heavier elements in levels that approximate their abundance like the Sun. However, they consist mostly of hydrogen, about 90%, and helium, up to 9%. These are youngest stars, including the Sun. The Earth's Sun is an example of a metal-rich star and is considered as an intermediate population 1 star. While the solar-like Moire is much richer in metals. And because of high metallicity of population 1 stars makes them more likely possesses planetary systems than the other 2 populations. Because planets, particularly terrestrial planets, are thought to be formed by the accretion of metals. However, observations of the Kepler dataset have found smaller planets around stars with a range of metallicities. While only larger, it concentrates potential gas, giant planets around stars with relatively higher metallicity, like our Jupiter. This was the journey from creation of universe to birth of our wonderful tiny blue planet, the Earth. But still now, some unsolved question.
Why does time have a direction? Why did the universe have such a low entropy in the past? And time correlates with the universal, but not local, increase in entropy from the past and to the future, according to the second law of thermodynamics. Why are CP violations observed in certain weak force decays, but not elsewhere? Are CP violations somehow a product of the second law of thermodynamics, or are they a separate arrow of time? Are there exceptions to the principle of causality? Is there a single possible past? Is the present moment physically distinct from the past and future? Or is it merely an emergent property of consciousness? What links the quantum arrow of time to the thermodynamics arrow? In coming episode, I will come with a very interesting documentary, The Entropies of Arrow of Time. Till now, thanks for watching my video.